This video was sponsored by Incogni. Whenever we need a program to pause before running the next line of code, the sleep function is usually the go-to solution. It's available in pretty much every mainstream programming language, except JavaScript, where you have to jump through a few hoops. But hey, JavaScript is, well, JavaScript. But have you ever wondered why it's almost always called sleep? Why not wait or delay? Today, we're going to explore both software and hardware concepts to understand what really happens under the hood when a program calls sleep. Hi friends, my name is George, and this is Core Dumped. How could we build a hardware timer? Well, there are multiple ways to do it, but the first one that comes to my mind is by using flip-flops. A flip-flop is simply a memory cell made of transistors that stores an input value, but it only accepts this input on a rising or falling edge, depending on the type of flip-flop, rather than relying on a constant value like regular latches do with a write-enable signal. In my video on how the clock tells computers to move one step forward, we talked about JK flip-flops, a special flip-flop that toggles its value every rising edge when both J and K input are set active. We discussed that if we connect multiple JK flip-flops in a certain configuration, we get a counter circuit, a circuit that increments a stored value by 1 every time it receives a signal, like from a push button. If we feed a timer signal into this circuit, we essentially get a circuit that counts time. For example, if the clock oscillates at 1 Hz, the circuit effectively counts seconds, resulting in a sort of primitive electric stopwatch. But what we want is the opposite, a timer. It turns out that if we wire the flip-flops in the opposite way, we get the reverse effect. Instead of incrementing the value stored in the flip-flops, the value decrements on each clock cycle. And that's what a timer does. In this example, the count decreases by 1 each second. Of course, a timer is much more useful when we can set its initial value, and we can achieve that with just a bit of extra logic. In this example, I'm using a general set line to avoid both J and K on each flip-flop to be active at the same time. This allows us to control whether only J or only K is active, depending on the bit value we want to set in each flip-flop. Instead of toggling the flip-flops, the next rising edge of the clock causes all of them to load and store a specific value, the one we're passing in. That way, the timer starts counting down from this specific value rather than from its maximum possible value. With additional logic, we can also detect when the timer reaches 0. This can activate a signal on a wire, which in turn can be used as a source of interrupts. So when a process calls sleep, the operating system can be invoked through a system call. It sets the timer, and when the timer reaches 0, a hardware interrupt is triggered, causing the OS to resume the process that originally called sleep. But here's the catch. A timer is a hardware resource. We can't just create more of them at runtime. If a chip only has 2 embedded timers, then only 2 processes can use them at once. A third process, calling sleep, would have to, somewhat ironically, wait for one of the timers to become available before it can start waiting for its own time to pass. Clearly, such limitations don't scale well in a general-purpose operating system. So let's leave the hardware behind for a moment and explore pure software solutions. But before that, a quick message from today's sponsor, Incogni. Who hasn't received spam calls or sketchy emails lately? It's become so normal that we almost forget how dangerous it can be. Scams, phishing, fraud. It only takes one slip to cause serious damage. But what if you could stop those calls and emails before they even happen? Let me introduce you to the real problem, data brokers, the hidden middlemen behind all of it. These companies collect your personal data, not just your name and number, but your address, job history, health info, even financial and political details, and sell it to marketers, advertisers, and yes, scammers. And is not only about scams. Companies like your insurance provider can buy info about your habits or purchase history to find ways to charge you more or push expensive premium products. That's where Incogni comes to the rescue. You sign up, authorize them to work on your behalf, and they contact data brokers to request your data be removed, and they keep following up so it stays that way. The whole process is automated, and you get updates showing how many requests have been sent, completed, or still pending. I won't claim I was flooded with spam calls, but they definitely popped up now and then. Since using Incogni, I've noticed a real drop. And let's be honest, one scam call is all it takes to ruin your day, or worse. What I really like is that Incogni doesn't just do a one-time sweep. They keep checking back to make sure your data doesn't get relisted. It's ongoing protection, not a quick fix. If you value your privacy and want to support this channel, there's a link in the description. You'll get a big 60% discount on the annual plan, which is what I use and recommend, since it gives ongoing protection. Alright, back to the video. We're going to use one of the most basic principles in computing. The CPU needs a clock to run code. In a previous episode, we learned that this clock acts like a heartbeat, telling the CPU when to move to the next step in the code it's executing. Let's say the processor executes one instruction per clock cycle, and the clock is running at 1 kHz. So running 1,000 instructions would take exactly 1 second. If we wanted to create a delay in our code, like a custom sleep function, the simplest method would be to use a loop that does absolutely nothing. It just burns clock cycles until the loop exits, and by then, the desired time has passed. Most CPU architectures have a NOP instruction, short for no operation. It literally tells the CPU, do nothing. Just wait 1 clock cycle and move to the next instruction. If you're not into systems programming, what I'm doing here is explicitly controlling which instructions run inside the loop. But this approach gets tricky right from the start. Since the loop needs to evaluate a condition, it's not just the NOP instruction being executed. There are 3 additional instructions involved in each iteration. Since we're assuming each instruction takes 1 clock cycle, we can use that to calculate how many iterations we need to reach a specific delay. If we want a delay of, say, 32 milliseconds, we'd need at least 8 iterations. This method is called busy waiting, using CPU time to do nothing but wait. However, the initial setup before entering the loop also takes time. So, our function won't be very precise, especially for short intervals. Plus, the loop only checks the condition every 4 cycles, adding more inaccuracy. Sure, I could spend 30 minutes fine-tuning this, but it's not worth it. There are a lot of reasons why busy waiting is a bad idea in general-purpose systems. For one, we're assuming the CPU runs exactly 1 instruction per cycle, and that's just not true. Some instructions, like the div instruction, are more complex and require multiple steps. Because division is a more complex operation than addition or subtraction, many CPUs implement it using iterative algorithms, which require multiple steps. The number of steps often depends on the bit length of the operands or how quickly the algorithm converges to a result. So unlike add or sub, div often can't be completed in a fixed number of clock cycles. If that's not bad enough, clock speeds vary between systems. This line of code might delay for 1 second on one system, but on a faster machine, it could be a fraction of that. And on modern CPUs, clock speed isn't even constant. Under heavy load, the system can boost clock speed to complete tasks faster. But if the CPU gets too hot, it can throttle down to cool off, slowing everything down. And the biggest problem with busy waiting? It wastes the CPU, because the time it takes to run the loop is time other processes could use to complete important tasks faster. If you've watched my video on CPU scheduling, you'll remember that processes spend most of their time cycling between 3 states: ready, running, and waiting. When a process needs I/O, like reading a file or waiting for a network request, it enters the waiting state using a system call, voluntarily invoking the operating system so it can put the process in the waiting queue, freeing the CPU so it can run something else in the meantime. Once the I/O finishes, the process goes back to the ready state, but it won't run immediately. It has to wait in the queue until a CPU is free. Thankfully, most processes only need the CPU for very short bursts, so the CPU switches between them rapidly, giving the illusion that everything is running at once. But in non-preemptive systems, busy waiting is a real issue. If a process hogs the CPU to wait using a loop, no other ready process can run. It effectively freezes the system for the duration of the loop. This is terrible for concurrency. A single process trying to wait can block everything else from running. Programs relying on very long or even infinite loops are not uncommon, though. That's why preemptive operating systems exist. They solve this problem using a hardware timer, like the one we built earlier. I'll attach a fraction of my CPU scheduling video here to show how it works. A small unit of time called a time quantum or time slice is defined. Here in this animation, I'm using a time quantum of 100 milliseconds. New processes are added to the tail of the ready queue. The CPU scheduler picks the first process from the ready queue, sets a timer to interrupt after one time quantum, and dispatches the process. One of two things will then happen. The process may have a CPU burst of less than one time quantum. In this case, the process itself will release the CPU voluntarily. The scheduler will then proceed to the next process in the ready queue. If the CPU burst of the currently running process is longer than one time quantum, the timer will go off and will cause an interrupt to the operating system, forcing a context switch to be executed, and the process will be put at the tail of the ready queue. The dispatcher then selects the next process in the ready queue. This routine is applied consistently to every dispatched process, ensuring that no single process can hold onto the CPU for long periods or indefinitely, which prevents other processes from being starved of CPU time. Something very important to mention is that the timer is a physical device, usually embedded in the CPU circuitry. Notice that this safety net makes busy waiting even less reliable. Now the delay depends not just on clock speed or instruction timing, but also on how the OS schedules tasks and handles interrupts. Also, no matter what scheduling algorithm is being used, busy waiting is incredibly inefficient. And this is something you can test yourself. If you run a long busy waiting loop and check your system's resource monitor, you'll see one CPU core pegged at 100%, fully occupied by a process that's just waiting. Since the process is always ready to keep running the loop, it immediately takes over the CPU whenever it's available. The question here is, does a simple task like causing a delay in our program really need that kind of attention? You might be wondering why I bring up all the CPU scheduling stuff again. And the answer is simple, because the real solution to this delay problem is built on top of CPU scheduling itself. What if, instead of making the CPU burn clock cycles doing nothing, we simply told it, "Hey, I want to wait for a while. Go do something else in the meantime." In other words, we could have the process enter the waiting state for the amount of time it requested when calling the sleep function. While it waits, other processes can use the CPU, no time wasted. But this brings us back to a hardware limitation we mentioned earlier. If multiple processes call sleep, and the system only has a limited number of physical timers, what then? Well, just like CPU scheduling lets multiple processes share a single processor, we can use software to let multiple processes share one timer. For this part of the video, we need a way to track time. If you're not familiar with how computers measure time, it's actually pretty simple. We define a starting point called the epoch, and then we count time units from there. When we ask, "What time is it?" the system returns how many units have passed since that epoch. One of the most widely used epochs, maybe the most used, is the Unix epoch, which starts at midnight January 1st, 1970. In JavaScript, for example, date.now returns a really big number. That's just the number of milliseconds since the Unix epoch. To avoid dealing with big numbers and for simplicity, I'll assume our example begins at time 0, and the timer runs at 1 Hz, so we can track time in discrete seconds. We also want to distinguish between processes waiting for I/O and those waiting on a timer. So, any process that calls sleep gets added to a special list I'm calling the sleeping queue, which you will also hear me refer to it as the sleeping list. Let's walk through our example. At time equals 1, a process calls sleep for 10 seconds. We store two values for it, the time it called sleep and how long it wants to wait. And the operating system sets the timer to 10 seconds. Then, at time equals 4, another process also calls sleep for 10 seconds. Even though they both want to wait 10 seconds, the timestamps help us determine exactly when each one should wake up. Eventually, the timer goes off, triggering an interrupt that invokes the operating system. The OS checks the sleeping queue and moves any process whose wait time has expired back into the ready queue so it can run again. We're not done, though. There may be other processes still sleeping. Thanks to the timestamps, we can calculate how much longer each one has left. In our example, the second process still needs to wait 3 more seconds, so the OS sets the timer for that amount. When that timer expires, another interrupt fires, and the OS wakes up the next process and schedules it for execution. And that's how a single timer can manage multiple sleeping processes, with a little help from software. But let's keep going. There are a few edge cases we need to consider. Suppose a process arrives at time equals 16 and asks to sleep for 25 seconds. 4 seconds later, another process arrives and requests to sleep for just 8 seconds. Now, the timer is still set for the earlier process, meaning it won't go off for another 21 seconds. But we now know a different process needs to wake up much sooner, so the OS must reset the timer. To handle this efficiently, it's a good idea to keep the sleeping list sorted by wake-up time. That way, when the timer goes off, we're guaranteed that at least the first process in the list needs to be awakened. Before I explain why I said at least, keep in mind that I'm using a simple list here for the sake of explanation. It keeps things easier to follow. In real-world implementations, don't be surprised if you find complex but more efficient data structures, like red-black trees being used instead. Now, the reason I say at least the first process is because multiple processes can be scheduled to wake at the same time. So when the timer triggers the interrupt, the OS needs to keep checking the queue and continue waking up processes until it finds one that still has time left. In real systems, where time is tracked in microseconds and timers run at high frequencies, this rule matters even more. While the OS is busy waking one process and getting it ready to run, others in the queue might also reach their wake-up time. So the OS needs to check and wake all processes whose timers have expired by the time it finishes handling the interrupt. Another thing to consider is that once a process is removed from the sleeping queue, it's placed into the ready queue, which might already contain other processes waiting for the CPU. From that point on, it's up to the operating system and its scheduling policy to decide when the process will actually be dispatched to continue running. In my video about CPU scheduling, I mentioned that modern processors are so fast that the ready queue is often empty. This means that when a process wakes up, it's very likely to run immediately. However, if the system is under heavy load and there are many processes competing for the CPU, that precision can drop, and the delay before the process actually runs may increase. If you look up general information about the sleep system call, you'll find that the time you provide is usually treated as a minimum, not a guaranteed wait time. Ultimately, the chance that a process ends up waiting slightly longer than requested depends on several factors. I recommend pausing the video to read through this slide for more context. Believe it or not, knowing this can save you a lot of trouble if you ever run into timing issues in a project. You have no idea how much time I lost in my early days as developer simply because I had no idea this was a thing. If you're running a Python program, for instance, the overhead from the interpreter alone can introduce small delays that affect timing accuracy. The key takeaway here is that general-purpose operating systems don't guarantee precise timing. Their internal time resolution typically ranges from 1 to 10 milliseconds, depending on the platform and configuration. That level of precision is usually more than enough for user programs running on general-purpose systems, which, I must explicitly mention, are not real-time operating systems. So, how does the sleep function work? To sum it up, it makes a system call telling the operating system, "Hey, I need to wait for X time units before executing my next instruction. Instead of wasting CPU time, I'm voluntarily giving up the CPU so others can use it, as long as you promise to wake me up after at least X time units." And that's it. Hopefully, now you understand why the function that causes a delay is called sleep instead of wait in almost every operating system and programming language. Wait is a generic term. It implies a delay, but not how it's handled. Sleep, on the other hand, is more specific. It implies that the process enters a passive state, staying out of the way and not interfering with the rest of the system while it waits. Let's wrap things up for now. There are more exciting topics coming soon, so make sure to subscribe. You won't want to miss it. If you enjoyed this video or learned something new, please hit the like button. It's free, and it helps me out a lot. See you in the next one.